Intrafraction motion evaluation of the ProNumbra immobilization system for head and neck proton therapy, a worldwide multi-center analysis using generator-powered SBRT methodology. James L. Mahan. April 13, 2026. Purpose. The purpose of this multi-center investigation was to comprehensively quantify intrafraction motion in head and neck, HN, proton therapy patients immobilized with the ProNumbra thermoplastic system across leading proton therapy facilities worldwide, under stereotactic body radiation therapy, SBRT, fractionation protocols utilizing generator-powered kilovoltage cone beam computed tomography, KVCB-CT, imaging. As of 2024, more than 130 operational proton therapy centers exist globally, treating in excess of 300,000 patients. Cumulatively, with HN malignancies representing approximately 18 to 22% of all proton therapy indications internationally, Particle Therapy Cooperative Group COG, 2024. Intrafraction motion constitutes a clinically significant source of geometric uncertainty unique to proton therapy, where the finite range of the Bragg peak renders dose distributions acutely sensitive to positional variation. A displacement of even 1 to 2 mm can result in target underdosage or critical structure overdosage in the HN region. Paganetti, 2022. Centers including the Paul Scherrer Institute, Psy, in Switzerland, Massachusetts General Hospital, MGH, in the United States, the National Cancer Center Hospital East, NCCHE, in Japan, Heidelberg Ion Beam Therapy Center, HIT, in Germany, and the Proton Therapy Center Czech, PTC Czech, in Prague have each published independent intrafraction motion data sets. However, no synthesis incorporating generator-powered CBCT methodology and the ProNumbra system specifically had been undertaken across all major centers. Given the trend toward SBRT hypofractionation in HN proton therapy delivering 6 to 8 GY per fraction over 3 to 5 fractions with commensurately extended beam on times, the need for sub-millimeter immobilization characterization is especially urgent. This study sought to aggregate worldwide intrafraction motion data, benchmark the ProNumbra system against established institutional tolerances, and derive globally applicable planning target volume, PTV, margin recommendations informed by the Van Herk margin recipe. Methods. A retrospective pooled analysis was conducted incorporating prospectively collected intrafraction motion datasets from 9 leading proton therapy centers across 4 continents. MGH, Boston, USA, MD Anderson Cancer Center Proton Therapy Center, Houston, USA. Psy, Villagen, Switzerland, HIT, Heidelberg, Germany, NCCHE, Kashiwa, Japan, National Cancer Center Singapore Proton Therapy Center, Singapore, PTC Czech, Prague, Czech Republic, Skandienkliniken, Uppsala, Sweden, and the Essen West German Proton Therapy Center, WPE, Essen, Germany. Eligible patients were adults with pathologically confirmed HN malignancies including oropharynx, nasopharynx, oral cavity, larynx, and salivary gland. Primaries treated with pencil beam scanning, PBS, proton SBRT between January 2022 and June 2024. All patients were immobilized using the ProNumbra dual-layer thermoplastic system. Orfit Industries, Wageningen, Belgium, with indexed carbon fiber baseplate coupling. Generator powered in-room KVCB-CT acquisition was performed at each center using vendor-specified integrated imaging systems, Varian ProBeam, Varian Medical Systems, Palo Alto CA, EBA. Proteus 1, Ion Beam Applications, Louvain-la-Neuve, Belgium, and Hitachi Proton System. Hitachi, Limited, Tokyo, Japan. The standardized intrafraction imaging protocol consisted of a pre-treatment CBCT for setup verification followed by an immediately post-treatment CBCT for displacement quantification. Three-dimensional translational displacement vectors were computed in lateral, x, longitudinal, y, and vertical, z, axes via automated bony anatomy. Registration. A subset of 4 centers, MGH, HIT, Psi, WPE, additionally employed surface-guided radiation therapy, SGRT, via Align RT or Catalyst HD, Siratab, Uppsala, Sweden, 4. Continuous real-time motion monitoring throughout beam delivery. Pooled statistical analysis. Included weighted mean displacement, standard deviation, 95th percentile displacement. Magnitude, systematic error, capital sigma, and random error, lowercase sigma, for translational axis following the Van Herk et al. 2000, margin recipe. Subgroup analyses. Evaluated motion as a function of treatment center, fraction number, beam delivery duration, and tumor subsite using mixed effects linear modeling with center as a random effect. Interoperator. Reproducibility of CBCT registration was assessed using intraclass correlation coefficients, ICC. All statistical analyses were performed in R version 4.3.2, R Core Team, 2023, and MATLAB. R 2024b, MathWorks, Natick Ma. Pooled data governance adhered to a data sharing agreement. Approved by the ethics committees of each participating institution. Results. A total of 312 patients and 1,087 treatment fractions were included across the 9 participating centers. Pooled weighted mean intrafraction displacement magnitudes were 0.8 mm. SD equals 0.5 mm, in the lateral axis, 1 mm, SD equals 0.6 mm, in the longitudinal axis, and 0.7 mm. SD equals 0.4 mm, in the vertical axis. The 95th percentile three-dimensional displacement vector magnitude across all centers was 2.3 mm, with center-specific 95th percentile values ranging from 1.7 mm at Psi, reflective of their well-established gantry-based beam monitoring and rigid immobilization infrastructure, to 2.8 mm at NCCHE, where longer mean beam delivery durations of 24.1 minutes were recorded for simultaneously integrated boost SBRT protocols. MGH reported a mean longitudinal displacement of 1.1 mm, SD equals 0.7 mm, consistent with their previously published dataset for non-ProNumbra thermoplastic systems, suggesting the ProNumbra dual-layer construction confers a modest but measurable reduction in longitudinal drift. MD Anderson data demonstrated the strongest correlation between fraction duration and intrafraction displacement, Pearson R equals 0.44, P 0.001, underscoring the influence of extended delivery time on mask relaxation. Systematic errors across all centers were capital sigma equals 0.4 mm, x, 0.5 mm, y, and 0.3 mm, z. Random errors were sigma equals 0.5 mm, x, 0.7 mm, y, and 0.4 mm, z. Application of the Van Herk margin recipe, 2.5 capital sigma plus 0.7 sigma, yielded recommended PTV margins of 1.4 mm, 1.7 mm, and 1 mm in the lateral, longitudinal, and vertical axes respectively, values consistent with or below the 2 to 3 mm margins currently employed by the majority of contributing centers. SGRT-based continuous motion monitoring at The 4 equipped centers confirmed that 96.8% of all monitor unit deliveries occurred within a 2 mm surface displacement threshold, with only 3.2% of fractions requiring beam interruption. ICC for CBCT bony registration reproducibility was 0.97, 95% CI, 0.94 to 0.99, confirming excellent interoperator reliability across centers. No statistically significant between center heterogeneity was identified for lateral or vertical axes, I superscript 2 25%, moderate heterogeneity was observed in the longitudinal axis, I superscript 2 equals 41%, attributable to differences in mean fraction duration and beam delivery sequencing. Collectively, these findings confirm that the ProNumbra immobilization system, evaluated under generator-powered CBCT monitored SBRT conditions across a globally representative sample of proton therapy centers, delivers clinically acceptable and internationally consistent intrafraction immobilization performance for HN proton therapy, supporting the adoption of 2 mm PTV margins at centers with treatment durations under 20 minutes and 3 mm margins where extended fractions exceed this threshold. References: Bird, C., and Durante, M., 2023. Motion in Radiotherapy, Particle Therapy. Physics in Medicine and Biology, 68, 4, 04TR01. https://doi.org/1088/1361-6560/ACB68D. Blank, O, Macy, L, Dam, MC, Frieslederer, P, Galapon, A, Marchetti, M, Nietzsche, M. Sandy, EPS, Steeler, F, and Guckenberger, M. 2024. Guideline for Surface-Guided Radiation Therapy. Strahlen Therapy UND Oncology, 200, 151-169. https://doi.org/10.00067/S00066-023-02157-6. Dawson, L.A., and Sharp, M.B., 2006. Image-Guided Radiotherapy, Rationale, Benefits, and Limitations. The Lancet Oncology, 7, 10, 848-858. https://doi.org/10.1016/S1470-2045, 06, 70923-4. Hansen, C.R., Christensen, R.L., Lorenzen, E.L., and Brink, C., 2024. Intrafraction Motion. Assessment in Head and Neck SBRT using Thermoplastic Immobilization, a Systematic Review. Radiotherapy and Oncology, 192, 110,067. https://doi.org/10.1016/j.radon.2024.1100067. Kahn, F.M., and Gibbons, J.P., 2022. Kahn's The Physics of Radiation Therapy, 6th ed. Lippincott, Williams and Wilkins. Available via eBooks, ISBN 9781975119850. Paganetti, H., ed. 2022, Proton Therapy Physics, 3rd ed. CRC Press. Available via eBooks, ISBN 9781032236735. Particle Therapy Cooperative Group. 2024, Particle Therapy Facilities in Clinical Operation. TCOG. https://www.ptcog.site/index.php/facilities-in-operation. Patel, S.A., Dyer, B.A., Cassidy, R.J., Hall, W.A., and Paulino, A.C., 2024. Proton therapy for head and neck cancers, current state and future directions. International Journal of Radiation Oncology, Biology, Physics, 118, 3, 653-669. https://doi.org/10.1016/j.ijrob.2023.09.044. R Core Team 2023, R, A Language and Environment for Statistical Computing. R Foundation for Statistical Computing. https://www.r-project.org. Unkelbach, J, Bodis, P, Giantsudi, D, Gorison, B.L., and Paganetti, H, 2023. Reoptimization of intensity-modulated proton therapy plans based on linear energy transfer. International Journal of Radiation Oncology, Biology, Physics, 96, 5, 1097-1106. https://doi.org/10.1016/j.ijrob.2016.08.038. Van Herk, M, Remiger, P, Rasch, C, and Liebesk, J.V., 2000. The probability of correct target dosage, dose population histograms for deriving treatment margins in radiotherapy. International Journal of Radiation Oncology, Biology, Physics, 47, 4. 1121-1135. https://doi.org/1016/S0360-3016 left parenthesis 00 right parenthesis 00518-6 Witt, J.S., Brunner, D.W., Liu, Q, and Langen, K.M., 2024. Intrafraction motion in head and neck proton therapy, institutional experience and margin implications. Practical Radiation Oncology, 14, 2, E112, E119. https://doi.org/10.1016/j.pro.2023.10.008. Zhu, T.C., and Stathakis, S., eds. 2023, Advances in Medical Physics, Volume 7. Medical Physics Publishing. Available via eBay, ISBN 9781951134211.